Okay, so we're going to continue talking about integral domains for at least this video. There's a few more results I want to mention and a couple more definitions I want to mention, and then I'll have a list of problems from chapter 13, I believe it is. Okay, so there was one thing I said I was going to prove in one of the previous videos, but I forgot when I ended the video. So it was about polynomial rings. If D is an integral domain, so if you already have an integral domain, then if you form its polynomial ring, that polynomial ring is also an integral domain. I said this and I said I'd prove it, but I never came back to that. Okay, so we assume D is an integral domain. I'm not going to write that. That tells us the three things, right? Tells us it's commutative. It's a commutative ring. It has a unity element, and it has the no zero divisors property. So I have those three properties to work with. To show that dx is also an ID, well, commutative is automatic because the polynomial multiplication is based off of multiplication in the original underlying ring, and that's commutative in this case. So we don't need to check that. It's commutative. Does it have a unity element? Well, it's got 1D as the constant constant polynomial 1D. So it has no x's. It's just that single constant term, or a constant polynomial. So like in Zx, the integer polynomial ring, the unity element is just 1. The polynomial 1. The degree 0 polynomial 1. So that's our unity element. So it's a commutative ring with unity. Now we just have to prove the no zero divisors property. And the way I want to do it is, let's assume we have two non-zero polynomials. So assume f of x and g of x are elements of dx. So they're polynomials with coefficients coming from D. And we're assuming they're non-zero polynomials. Remember, there's different ways you can state the no zero divisors property. One way is if I have two non-zero things, their product has to be non-zero. Two non-zero elements can't multiply to be 0. So let's prove that happens in this case. If I have two non-zero polynomials, their product is also a non-zero polynomial. So I can write them then as polynomials with a non-zero leading coefficient. Let's use a's for f of x. And b's for g of x. So f of x is going to be a degree n polynomial. It'll have x to the n as its largest power. G of x might be a different degree, so let's say m, b sub m, x to the m, all the way down to b1x plus b0, where all the a's and b's are in D. The ai and bj are all in D, and in particular, an and bm are not equal to the 0 element of D. Okay, so if these are non-zero polynomials, then we can say at least their leading term is non-zero. Some of these lower degree terms might be 0, but at least the largest degree terms are non-zero. Okay. So then what happens if I multiply them? I guess. So therefore, f of x, g of x, if I multiply this times this, there's going to be a ton of terms. I'm not going to write them all out, but if you think of it, every term from f of x has to equal, or has to be multiplied by every term of g of x. And so in particular, the leading terms have to be multiplied, and that's going to be a n bm x to the n plus m. And it'll have a bunch of lower degree terms, but this is the n plus m term. And its coefficient is an bm. Now since an and bm are not 0, and d, the place where these things live, these coefficients live, d is in the integral domain, then multiplying two things in d that aren't 0, that product will not be 0. So we know a and bm is not the 0 element. Alright, so therefore, f of x, g of x, f of x times g of x is not the 0 polynomial. It's not the 0 polynomial. So if I have two non-zero polynomials, their product will not be a 0 polynomial. So the product will still be non-zero. And that proves that this polynomial ring has the no zero divisors property. So therefore, dx is an integral domain. Okay. So I mainly include this proof, not because I expect you to reproduce it or anything, but it is important to remember that if you're trying to come up with different types of different examples of different types of rings, so integral domains, and you want different examples, you want to be able to take polynomial rings to get like more varied examples. So just remember that if you already have an integral domain, then its polynomial ring will also be an integral domain. All right, that's one thing out of the way. Let me, before I forget, tell you a couple definitions. So in the problems I want to assign, there are a couple words that come up. They're not going to be that important to remember the definition, but just so you can answer the questions that are asked, because I want you to think about these concepts. In a ring, R, or an element A is called nilpotent if a to the nth power equals 0 for, or 0 sub r, for some I guess natural number in. So if you look at powers of that element, you eventually hit 0. So for example, in Z8, if I look at 2, we've got 2 to the first is 2, 2 squared is 4, 2 cubed is 8, but in Z8 we're doing operations mod 8. 2 cubed is 0. If I keep going, 2 to the fourth Well, that's going to be 2 times 0 now, which is still 0. So once you get 0 as a power, every power after that's also 0. So 2 is nilpotent in Z8. But some other elements, this won't ever happen. If we look at 3, for example, I'll write these out, but it's not really necessary. 3 squared would be 9, which mod 8 is 1. 3 cubed would be 3 again. 3 to the 4th would be another 3, make 9, which is 1 again. So powers of 3 are going to alternate between 1 and 3. So 3 is not nilpotent. Nilpotent. Okay, so I mentioned this definition again, not because it's one that you have to memorize, but there's going to be a homework question that asks you to figure out what are the nilpotent elements of certain rings. Another definition, an element A is idempotent. If A squared equals A. So for example, if there's a unity element, 1, the 1 sub r, 1 squared is always 1, because it's the multiplicative identity. 0 sub r, 0 times anything is always 0, so 0 is also idempotent. So 1 and 0 are always idempotent. And in most number systems that we're used to, that's it. If A squared equals itself, then A has to be 1 or 0. But we can come up with other examples. So for example, in Z plus Z, if I look at 1, 0 and I square that, well, in the first quarter I get 1 times 1 is 1, and in the second quarter I have 0 times 0 is 0. So this ordered pair squared is itself. So that's an idempotent. And I'm having second thoughts about the grammar here. Sometimes you see these as adjectives, idempotent element. Some places you'll see something is an idempotent. So I could say it is an idempotent as a noun. That's not a big deal either way. Okay, so again, nilpotent and idempotent, those are just 2 words that you'll see in at least one of the homework problems I'll assign. It's just about thinking about specific examples. All right. Next, I want to talk a little bit more about characteristics. So remember, if R has a unity element, has a 1, then the characteristic is the first integer, the first positive integer in that makes the multiple of 1 equal to the 0 element. So it's how many times do I have to add 1 to itself before I get 0. If this never happens, so in many cases this never happens, in that case you'd say the characteristic is 0. Alright, so that was from the last video, but I wanted to talk more about it in the context of integral domains. If D is an integral domain, then the characteristic of D is either 0 or prime. So you couldn't have an integral domain with a characteristic of 6, for example, or 4. It has to be a prime number or 0. Okay, so let's suppose the characteristic of D is a number n. Where n can be factored. So where n's not prime. So say it can be factored as p times q. P and q are natural numbers and they're not equal to 1. So we have some non-trivial factorization of n. So this is going to be a proof by contradiction. We're assuming the characteristic is not 0 and it's not prime. So we're going to come up with a contradiction. Then, since the characteristic of D is n, that tells me n times 1 sub D, that's 0 sub D. But n can be factored. That's PQ. And we didn't dwell too much on proving properties of integer multiplication inside of a ring, but this could be written as PQ times 1D, 1D. And what you can do by using distributive properties and so on, you can prove a property that if you have a product of integers times a product of ring elements, I can put one of the integers with one of the ring elements and the other integer with the other ring element. Okay, so this is the same thing as P times 1 times Q times 1 equals 0. All right. So that tells us that we have a product of two ring elements. This is a ring element, and this is a ring element. Their product is 0. But we're in an integral domain. D is an integral domain. And if in an integral domain, if we have a product equals 0, that tells us one of the parts, at least one of the parts is 0 by the no zero divisors property. The only way to multiply to get 0 is if 0 is already involved in the product. So therefore, since D is an integral domain, P times 1 equals 0 or Q times 1 equals 0. But P and Q are both strictly less than n, because P and Q were proper factors of n. We found a non-trivial factorization. And that's a contradiction because the characteristic of D was n. And n, the characteristic, that's the first integer multiple of 1 that gives me 0. This is the first time I get 0. The first integer that gives me 0 in this kind of integer product. So let me erase and write that. So my subscripts. Either P times 1 equals 0 or Q times 1 equals 0. And that contradicts characteristic D equals n, because n, the characteristic, is supposed to be the smallest positive integer for which n times 1 equals 0. P and Q are both smaller than n, so we would have found a smaller integer that works. So therefore, the characteristic of D cannot be n. So in particular, what was special about n? It had factorization. So n was what we call a composite number. Composite just means not prime. Non-prime. So characteristic of D cannot be composite. Therefore, it either has to be prime or it has to be 0. It has to this never happens, which would be characteristic 0. So therefore, characteristic D is prime or 0. Okay, so in a general ring, you can have characteristic, any number could be the characteristic. You could have characteristic could be 8. The characteristic of Z8 is 8, and that's not prime. But that's only possible because Z8's not an integral domain. Okay. I guess the other thing I will prove in this video is a nice property about rings with prime characteristics. It doesn't necessarily have to be an integral domain, but let R be a commutative ring. That's all I need. Commutative ring. It doesn't necessarily even have to have a unity element for what I'm going to do. With characteristic equal to some P, where P is a prime, then for any elements A and B in R, A plus B to the P power equals A to the P plus B to the P. So the mistake everybody makes in algebra actually works. So again, we're in this very special situation where we're in a commutative ring that has a prime characteristic. So characteristic P. Then if I take a sum raised to that exact prime number power, I can distribute that exponent to the individual parts. Okay, I don't have to worry about the middle terms because all those middle terms are going to disappear. Okay, so let me just give you a quick indication of why this works, and then I'll illustrate it with an example. But suppose we have A plus B to the P power. Then what that means is A plus B times A plus B P times okay, so I don't want to write a formal proof of this. So let me just kind of sketch the thought process out. If I were to expand this, then multiplication is commutative, so it doesn't matter. I can FOIL this, and I don't have to worry about the order of multiplication. So let's think about what are the different possible types of terms. Think of these as variables, a and b. Well, what if I took only a's? I multiply all this stuff out, and I take only the a from each of the parentheses. And I have a times a times a, p times. So I get a to the p. That's the only way I get a to the p from this product, is if I take the a from each parentheses. Well, what's the next type of element I could get? I could take 1b and a to the p minus 1 a's. So from one parentheses I take b, and from the rest of the parentheses I take the a. That'll give me p minus 1 a's and a single b. Now, how many different ways are there of doing that? Well, there are p factors. I need to pick one of them to take b from. So there's p ways of doing that. So my coefficient for that term would be p. But the characteristic is p. That means multiplying a ring element by p kills it off. It becomes 0. So if I multiply something by p, that disappears. That's 0. All right. Now, we could do the same thing for any other possible term. So the next one would be b squared. I take 2b's and p minus 2a's. Well, how many ways are there of getting this combination? I have to pick 2 places to take b from. So this is what's called p choose 2. I don't want to, if you're in discrete, you've seen that already. But I don't want to get into the definition of that. But just know, p choose 2, that's the number of ways of choosing 2 things from p things. We have p parentheses, I need to choose 2 of them to take a b from. That formula involves multiplication by p. So it has a p involved, p times something else. So once I have that p, this is going to become 0, and that term's going to disappear. That will happen for every single possible combination of a's and b's, except for a to the p and b to the p at the end. All the middle terms will disappear because their coefficients will have a factor of p as part of them. And factors of p kill off ring elements in a characteristic p ring. Let's look at a specific example just to illustrate a little bit more clearly. So let's look at Z3. So in Z3, characteristic is 3. Suppose I had x plus y. I've changed my mind. I like x and y better than a and b. But it doesn't matter. Let's expand x plus y cubed. Let's actually multiply this out as if it was just integer coefficients. Then we'll see what happens when we do mod 3. So if I multiply this out, x plus y times x plus y will be x squared plus 2xy plus y squared. Now we're going to distribute x and y to it. That gives us x cubed plus 2x squared y plus xy squared plus x squared y plus 2xy squared plus y cubed. Now we combine our like terms. We have x cubed, 2x squared y plus x squared y, that's 3x squared y, plus xy squared, 2xy squared is 3xy squared, and then plus y cubed. Okay, so this would be the coefficients I get in the integer polynomials, but we're in Z3. So 3 turns into 0. These two terms disappear. I'm left with x cubed plus y cubed. So the middle terms disappeared because they got that factor of 3 as part of their coefficient. And this will always happen if my characteristic is prime and my exponent is that same prime number. So that illustrates what's going on. And in fact, let me just state a consequence of this. We can say something even stronger than that. So this is a corollary. Again, let's assume the characteristic of our commutative ring with unity is a prime p. Then, if I take one of these binomials and I don't just raise it to the p power, but I raise it to any power of that p, so x plus y to the power p to the n. So it's like you repeatedly raise it to that same p power, then I can just distribute that exponent. Okay, so it's basically it's basically an induction proof. Let me just illustrate one step of it. So what if I had x plus y to the p squared? That would be x plus y to the p to the p. Because if I raise something to a power, then another power, I multiply those powers, so that would give me p squared. But x plus y to the p, we already know from the theorem that I can distribute that p to these two parts. That's x to the p plus y to the p. But now I still have this other p to raise it to, but now it's just the same theorem again. I can distribute that p to this binomial. So it'd be x to the p plus y to the p. And now I multiply my exponents. That's x to the p squared plus y to the p squared. That's p squared as my exponent. Okay, so inductively we could do that with any exponent. Like p cubed, I just have another p on the outside, so I distribute it again. You can do it as many times as you need to and prove it. And by induction, it's true for any n. All right. So finally, double check I'm not forgetting anything else. That's everything I wanted to mention from the chapter 13 about integral domains. I will put up a list of problems at the end of this video to look at, and then pretty soon afterwards I'll post a quiz based on those problems. And then in my next video we'll talk about a couple other concepts from ring theory. So it'll be concepts that are drawn from chapters 14 and 15. Again, it'll be kind of a few things from both. We're not going to do too much with either of them. But it'll, again, be very similar to the last few things we did from group theory, which was all centered around homomorphisms. So we'll talk about ring homomorphisms and the corresponding notions about factor rings and the analogous concept to normal subgroups. So I'll have to define that next. But that's where we're headed. That's really all I intend to get through is what those topics from those two sections. All right, so I'll stop this video a little bit early since I don't want to mix my topics too much.